Today we look at surjective functions. So starting with a definition, we say that a function f that has a domain x and the range or the codomain is y. This function is called surjective or onto. So surjective and onto mean the same thing, surjective or onto. If for all y in y, so any element you pick in the codomain, there is an x that is mapped to that y. There is an x such that f of x is equal to y. Okay, so that means there are no elements here that are not a map from some element in there. So that is to say that f is surjective if and only if the range of f, which we write as the range of f, is equal to the codomain. The codomain of f. Again, then the codomain COD and then f. So if you're given a function, for example, here we have this function 1 determine whether this function, which is from a set of real numbers to the set of real numbers, such that f of x is equal to x squared plus 3 is surjective. So we want to check, is this function here surjective? What we need to do is check, is the range equal to the entire set of real numbers? So if the range is equal to the entire set of real numbers, then it means that it is surjective. What we need to do, find the range and then check, is it equal to R? So we know how to do that. We say we write y is equal to x squared plus 3, and then make x the subject of the formula. So this means x squared is equal to y minus 3, and x is equal to plus or minus the square root of y minus 3. Okay, and now here what you do is you look at what are the values of y that will give us the solution over here. So y can only be greater than, so the domain of this function here is that y is greater than or equal to 3. So if y is less than 3, then we are not getting a real number. Okay, so if y is less than 3, then we're not getting a real number here. So the domain of this function here is that y is greater than or equal to 3. But here our codomain says all real numbers. So here it's only numbers that are greater than 3. These two are obviously not equal. So we can see that the range of f, this is equal to y, such that y is a real number and y is greater than or equal to 3. This is definitely not equal to the set of all real numbers. So we can say that since the range of f is not equal to the codomain, then f is not surjective. Okay, so that's basically how we show that a function is surjective. Then number 2, we have a function, or we say, is this function that goes from the set of all real numbers except 0 to the set of positive real numbers, such that f of x is equal to 16 over x squared surjective. So is this function here surjective? So we have our domain, we have our range, positive real numbers. We need to check, is the range of this function here the set of real numbers, positive real numbers? If it is, then our function is surjective. So we find the range. So we say y is equal to 16 over x squared. Then this means that x squared is equal to 16 over y, and then x is equal to plus minus the square root of 16 over y. All right. Now we look at what are the values that y can take. Now, because we have y in the denominator, very important that y is not equal to 0, because if y is equal to 0, then this is obviously not defined. And because it is under the square root, we need 16 over y to be greater than 0. So I say strictly greater than because it cannot equal to 0, because 16 is not 0, so the denominator cannot be 0, so this must just be positive. Okay, then the only way for this to be greater than 0 is if y is greater than 0, because here I have a positive number, and if I want the whole fraction to be positive, I must divide a positive by a positive. If I say a positive divided by a negative, this is going to give me a negative. So this fraction is only positive if y is positive. So here are my two conditions. So y is not 0 and y is greater than 0. So this is just the entire set of positive real numbers. So our range of f, this is a set y. Y is a real number, and y is greater than 0. This is definitely equal to the set of positive real numbers. So we can say that since the range of f is equal to the codomain of f, then f is surjective. So that's basically all we do to check whether a function is surjective or not. You find the range, and then you compare the range with the codomain. If they're equal, the function is surjective. If they're not equal, then it is not surjective. Okay, and then another thing to take note of, the definition, is that a function which is both injective and surjective is said to be bijective. Okay, so it's bijective or it is a bijection. Okay, so it's bijective or it is a bijection. Right, that's just the definition to take note of. Then the next thing we look at is the algebra of functions. Now, with functions, just like numbers, functions can be combined. Can be combined. means of addition, subtraction, multiplication, and division. Okay, so just like numbers, we can combine fractions using arithmetic operations. So the first one is we have f plus g of x. What this means is you take f of x, then you add g of x, then that is what f plus g of x. So take f of x, take g of x, add them together. Subtraction works the same way, f minus g of x. This is f of x minus g of x. So basically you take x, your x value substituted into the function f, your x value substituted in the g function, and then you subtract. Then number 3, we have a product, we have fg of x. This means f of x multiplied by g of x. So substitute into f, substitute into g, and then multiply. Then division is the same, f of g of x. This means f of x over g of x, except here there's a condition where g of x is not equal to 0 because we're not allowed to divide by 0. And then we have cf of x. So we can also multiply a function by a constant. So this is a constant multiplied by f of x. Okay, and here just take note that c is a real number. Then another operation that can be done with functions is what we call the composition of functions. So with composition of functions, basically what we're doing is that one function is the input of another function. So instead of inputting a number like 1 or 5 or even just x, you input a whole function into another function, and then the procedure is done in pretty much the same way. So we have a definition here. We say that if f and g are functions, the composition of f and g or we say the composite function and then we write it like this. F is a circle here, and we read this as f composed with g is defined as follows. So f of g of x, this is f of g of x. So what this means is that into the function f, your input is not just x itself, but it is the function g of x. Then we say the domain of the composition f of g consists of the numbers x in the domain of g for which g of x lies in the domain of f. Okay, so this may sound pretty complicated, but if you have your function f is a function from a to b, and g is a function from c to d. Now g because you're working out g of f of x, it means what you're putting into f came out of g. So it came out of g, so it's here. It is in the range of g that goes into f, and only the parts that are suitable, because the domain here is not necessarily the same as what you have over here. So if your output here gives you some numbers that do not work for this function, let's say, for example, this one is a square root function, square root of x, and this one here, you just have x plus 1. So here you can see that the output is real numbers. But here, when now you get an output here, since here you're just getting real numbers, not all the real numbers are going to be in the domain of the composition, okay? So you remove all those parts that come out of G that cannot go into F, basically. So it's going to be a subset of the range of F. Okay, so again, composition just means one function is the input of another. So whatever comes out of this function goes into that one. So we need to make sure before it goes in, if there are any numbers or any elements in the output that cannot go into this function, they are removed. That's basically what the sentence there is trying to say. Okay, so now we look at how we actually work out compositions. So an example, say that if f of x is equal to x squared and g of x is equal to x squared plus 1, f of g of x, this is f, and then into f you're going to put g of x. So that means into f, I replace this with what g of x is. This is x squared plus 1. And now this, I'm going to replace it with x in the function f. So instead of writing x, I put x squared plus 1, then everything else will remain the same. So this, by the binomial theorem, x to the power of 4 plus 2 x squared plus 1. Okay, and if I try it the other way around, g of f of x, this is g of f of x. So this time, f of x is going into the function g. What is my f of x? This is x squared. So that means in the function g, whenever I have x, I'm going to replace that x with x squared. So this gives me x squared plus 1, and this gives me x to the power of 4 plus 1. And here we can see that these are definitely not equal. So take note that in general, f of g is not equal to g of f. So there are obviously some cases where the two are equal, but in general, they are not equal. So number 2, we have f of x. This is equal to the square root of x, and g of x. This is equal to x minus 3. We want to work out f of g of x. That means into f, we are putting the function g of x. So we are putting x minus 3. And that means in this function where we have x, we are going to replace the x with x minus 3. So this is the square root of x minus 3. And then the other way around, g of f of x. So into the function g, we are putting the function f of x. So into the function g, our f of x is the square root of x. So that means in my function g, where I have x, I'm going to replace x with square root of x. So this is square root of x minus 3. Everything else that doesn't have an x remains the way that it is. Okay, then we have the domain of f of g. So if we look at this one here, this x must be greater than or equal to 3. And then the domain of g of f, here x must be positive. Greater than or equal to 0, actually. Then, of course, you can compose a function with itself. So note that the composition of a function with itself is called an iteration. Okay, so say that each output of an iteration is called an iterate. Okay, so that means you compose a function with itself. So the output of the function itself becomes its input. So you're like going around in a cycle. So you have a function, its output, and then becomes its input. An iterate where x1, this is equal to f of x naught. Then x2, this is equal to f of x naught. So this is just x1. So this is f of x1. So you have a starting point. This x naught will be given to you. You put it into your function. Whatever you get out, that is x1. Then to get x2, you put x1 into the function again, and that will give you x2. Then x3, this is f of x naught. So this is just f of x2. So whatever output you're getting, so x naught is given to you, and then you put it into the function. The output, you put it back in the function. The output, you put it back into the function, and so on. So those are your iterates. So we see an example. Says find the first 3 iterates of the first 3 iterates. We have x1, x2, and x3 of this function. F is equal to, sorry, I must say f of x. F of x is equal to 2x minus 3 for an initial value x naught is equal to 1. Okay, so we're given x naught, we need to work out x1, x2, and x3. So we say that x1, this is f of x naught. So our initial value, we just substituted into the function. So this is f of 1. That means wherever we have x in the function, we replace that with 1. So this is 2 times 1 minus 3, and this is minus 1. And then this minus 1 will go into the function again, and then we get x2. So x2, this is f of x1, which is f of minus 1. So that means wherever we have x, we replace the x with minus 1. So this is 2 times minus 1 minus 3, and this gives us minus 5. And then the last iterate, we have x3. This is f of x2. So x2 is minus 5. So this is 2 times minus 5 minus 3, and this gives us minus 10 minus 3, which is minus 13. And you can see that with this function, we can go on forever. Okay, so now that we know how to compose a function, it is interesting to know how do we decompose a function. So decomposing a function. So basically with decomposing a function, we're doing the opposite. With composing, you have two functions, you have f and you have g, and then you come up with a single function, and we call this function h. Now with decomposing, I give you a function h, and what you need to do is tell me two functions that when I compose them, they give me this function over here. Okay, so we say that writing a complicated function as a composition of two or more simpler functions is known as decomposing. Okay. Now what you should take note is this process is not unique. Note that this process is not unique. So that means the way you would decompose a function is not necessarily the way that I would decompose it, but when we come up with those two or more functions and then compose them, we still end up with the same result. So there isn't just one specific answer. So if we look at an example of this, we have h of x. This is equal to 2x minus 3 to the power of 5. And we say find f of x and g of x such that h of x is equal to f of g of x. So what we want to do is break down h into two functions that when we compose those two functions together, they give us h of x. So one simple way to do this is f of x. This is equal to x to the power of 5, and then g of x is equal to 2x minus 3. Okay, so of course you can test this out. So you can test and see if I work out f of g of x, is it going to give me this? So this means f of 2x minus 3, and this is what does f do? It raises it to the power of 5. That means wherever I have x, I'm going to replace that with 2x minus 3. So this is 2x minus 3 to the power of 5. Okay, so when you're given something complicated like this, try and imagine what is happening to x. So when x goes into the machine, it's first multiplied by 2, subtracting 3, and then raised to the power of 5. So those three things, you can obviously break it down into even three functions. The first one multiplies by 2, then the second one subtracts 2. So if you have your, I just want to show you that you can write it even with three functions. So the first function, the one that is going to be your initial input, let's say I call it k of x. So we say what's happening to x. To get this, first you multiply it by 2. So say multiply by 2. So this will write k of x is equal to 2x. And then after it's multiplied by 2, what happens? We subtract 3. So we can say g of x, the next step, we subtract 3. So this means g of x, this is equal to x minus 3. So here, your input is always x. It doesn't depend on what happened over here, because if I put this function into that one, the x is going to be replaced with 2x. So your input with the function at each step, when you're writing them like this, multiplied by 2, it's x that's multiplied by 2. When I'm saying subtract 3, it's x that is subtracting x, because your input for a function is always x. And then the last step, f of x, what is happening? Raised to the power of 5. Raised to power 5. Okay, so after it is raised to power 5, we can say f of x is equal to x to the power of 5. Again, it's x to the power of 5, not x minus 3. And now when you compose all these functions, you say that your h of x, this is equal to, f is the final one. Then inside f, you put g, and then inside g, you put k. So this is how you would write the same function as a composition of the 3 functions. You would say this is f of g of k of x. Okay, so like I said, this is not unique. So one person may write it this way, because when I do compose these 2 functions, they give me that. And another person could decompose it into these 3 and also get the same thing. Okay, so another example, number 2, we have h of x. This is equal to the square root of 1 minus x squared. So again, decompose this into 2 functions. Here your f of x can be the square root of x, and your g of x can be 1 minus x squared. So try and come up with more, or another way that you could decompose h into other functions, so that when you compose those, they give you this one. So just like I did it over here. So it's very important to understand what is happening to x. So when x goes in, it is squared, multiplied by minus 1, then plus 1, or you say 1 minus x squared. Okay, and then you take the square root. So if you understand what is happening to x, and then you describe them like I've done here, and then you write your functions, at each step it must be f of x, and then here you say raised to the power of 5, so it must be x to the power of 5, not whatever you did at the previous function. Then you could come up with several different ways that you could also decompose this function. Okay, then the next thing we look at what we call inverse functions. So we start with a definition. So we let f be a function from the domain of f to the range of f. This is the function, be a function. Then the inverse, or its inverse function, if it exists. So it doesn't always exist. That means not every function has an inverse. And we write it like, it looks like f to the power of minus 1. This goes from the range of f to the domain of f. So it goes in the other way around. So you see f goes from the domain to the range of f, but then the inverse goes from the range to the domain. And this is defined as f inverse of y. So here it's of y because in the range we have our y values. X is the input, y is the output, is equal to x. Okay, so we have the output, and then we find out what is the input. And this is if and only if f of x is equal. Hi. Good. Okay, if and only if f of x is equal to y. Then we say that for any x in the domain of f and y in the range of f. So that's just saying what I said over here. Y must come from the range because we know our domain, these are x values, and our range, these are our y values. Now, very important to note is that a function f has an inverse if and only if it is bijective. So if I ask you without working anything out, is this function, does this function have an inverse? All you need to do is check, is the function injective? Is the function surjective? If it is both, then the function does have an inverse. Okay, so if the function is not bijective, it does not have an inverse. So a few remarks. The first one is that F inverse reverses what F does. Okay. Then the second thing is that the domain of F inverse is the range of F. Then the third thing is very important to note is that F inverse is not equal to the reciprocal of F. That is not true, okay, in general. Okay, so when we are trying to find the formula for the inverse of x, what you need to do is you will replace f of x with y. You'll solve for x, interchange x and y, and then replace the y with f inverse of x. So we see some examples of how to do this. We have f of x, this is equal to 2x minus 3. The question says find f inverse of x. So to find f inverse of x, we said first you must replace f of x with y. So write y is equal to 2x minus 3. And then you interchange x and y, or basically just make x the subject of the formula. So what I'm going to do is I'm going to interchange where I have x, I put y, where I have y, I put x. So this is x is equal to 2y minus 3. And then I make y the subject of the formula. So 2y is equal to x plus 3, and y is equal to x plus 3 over 2. And now we say f inverse of x, this is equal to x plus 3 over 2. Okay, so another example, number 2, we have y is equal to x squared. And here we are told that x is greater than or equal to 0. So remember, because we're finding an inverse, our function must be bijective. And if this condition was not given, our function here would not be surjective. Okay, so we need to make it would not be injective, but not be one-to-one. So when x is restricted, then our function is now injective, and now it is bijective. Okay, so to find the inverse, we proceed in the same way. So here we have y is equal to x squared. Then we will interchange where I have y, I'll replace that with x. And where I have x, I replace that with y, and then I make y the subject of the formula. So this means y squared is equal to, y squared is equal to x. So y is equal to plus or minus the square root of x. Now here, you need to remember that the function must be one-to-one, so it cannot be plus and minus. Now remember what the initial condition was. The initial condition is that x must be positive. So we have a choice, either positive or negative. We must take the positive. So y is equal to the square root of x. Okay, so if here the condition was that x is less than or equal to 0, that means we want a negative output when we find the inverse. So here we'll say f inverse of x, this is equal to the square root of x. That's still for this one. But if in the question, the condition was that x is less than or equal to 0, then when we come to this part where we must choose either the positive one or the negative one, we need to remember that we should get a negative output, okay? And that is why our f inverse for this case, this will be minus the square root of x, because remember what a function and an inverse do. They reverse what the other one did. Okay, so if you put in negative, your output, when you reverse it, your output must also be negative, because the inverse gives you the input. Okay, the function itself gives you the output. It puts something in, you get an output, then the inverse takes that output as its input and gives you the input that you started with. Okay, all right, so just take note of that. And we have a definition here. So say that let f and g be functions of x, then f and g are inverses of each other. If and only if their composition, f composed with g, is equal to x, and g composed with f is equal to x. So that means if you compose f with g and also compose g with f, the answer is just x, then those two functions are inverses of each other. So we have an example here. Let f of x equal to 3x squared minus 1, and g of x equal to the square root of x plus 1 over 3. Now it says determine whether these two functions are inverses of each other. Determine whether the functions are inverses of each other. Okay, so how do we do that? We find f of g of x, and then we find g of f of x, and both of them must be equal to x. So we have f, inside f, we put the function g, so we put square root of x plus 1 over 3. So that means where we have x here, we're going to replace it with this square root. So we have 3, and then we have the square root of 3x squared minus 1. Sorry, what am I doing? Okay, so we have 3, yeah. Then we have the square root of x plus 1 over 3 squared minus 1. So here, square root and the squared cancel. So we have 3 multiplied by x plus 1 over 3 minus 1. Then these two will cancel. So I have x plus 1 minus 1. Minus 1 and plus 1 is 0. So I'm just left with x. So we can see that f composed with g gives me x. Now it's not enough to just show that in this direction it gives you x. You must show it in the function as well, g of f of x. So that means into the function g, you are going to substitute 3x squared minus 1. So this is the square root. So where you have x, you replace it with 3x squared minus 1. Then the plus 1 must still be there. 3 over 3 must still be there. Okay, then simplifying, this is the square root. Those two cancel. We have 3x squared over 3. The 3's will cancel. So I have the square root of x squared, which is just equal to x. Then we can see that since f of g of x is equal to g of f of x, and they're both equal to x, then you can say that f and g are inverses of each other. Okay, so a remark here. Now, in general, if f and g are injective functions, then we have that the inverse of their composition is equal to G inverse composed with F inverse. Notice how F and G have swapped places, and G of F inverse, this is equal to F inverse composed with G inverse. Okay, so very important to know that. Okay, so the next thing we look at the transformation of functions. Okay, so there are a few basic functions that you should know how to sketch. So what I would say is, if you do not know how to sketch these functions, please go and revise how to sketch these basic functions. So the first one is y is equal to x squared. Y is equal to x, a straight line. This is a parabola. Y is equal to the square root of x, the cubic one, y is equal to x cubed, and then y is equal to 1 over x squared, and then y is equal to the absolute value of x. So these are considered to be the building blocks of many other functions. And then we can create graphs of many functions by shifting these horizontally, vertically, stretching or shrinking them, as well as reflecting them along the axis. So these are like our starting points, and then we shift them either up or down. We shift them left or right. We rotate them about the x or the y axis, or we shrink them or stretch them, and then from there we come up with new functions. Okay, now the way this works, this is done. Okay, so the first transformation we look at, we say that if y is equal to f of x, then y is equal to f of x plus k. Shifts the graph of y is equal to f of x, up or down, by k units. So if k is a positive, then it'll shift it up. If k is negative, then it will shift it down. So for example, if we have the function y is equal to x squared, if we were to draw this one, like I said, it's a basic function. We have x and we have y here. So this is what it looks like. It's a parabola. So it continues like that. And then this is our graph y is equal to x squared. Now, if we want the function y is equal to x squared plus 2, what that means is this entire graph is shifted 2 units up. So every point here is shifted 2 units up. Every point is shifted 2 units up. And then you come up with a new graph like this that is 2 units above the other one. Okay, so this is the graph y is equal to x squared plus 2. So when the plus is here, the shift is in the y-axis. So if it was negative, it would be shifted down. So if you had x squared minus 2, then it's shifted 2 units down. Okay, number 2. This shift is called a vertical translation. So we say that this shift is called a vertical translation. Okay, then the second way that we can transform our basic graph, we say that if y is equal to f of x, then y is equal to f of x plus k shifts the graph k units left if k is positive and k units right if k is negative. Okay, so if we have the graph again, y is equal to x squared, and the graph y is equal to x minus 3 squared. So we ask ourselves, what is going to happen to this graph? So with questions like this, you need to be able to state what the transformation is, what actually happened to your graph, okay? Okay, so if we were to draw this one again, this is our x, that is our y. So the graph y is equal to x squared. It looks like that. Okay, my pen is acting up. So here we have x minus 3. So here, this is a negative number. So here, if you look at the rule, if it's negative, it means you shifted that many units to the right. So every point here on this graph is going to be shifted 3 units to the right. So this point here, which was at the origin, is going to shift somewhere here. It's now going to be at 3. And then this is your graph y is equal to x minus x minus 3 squared. Okay, so it obviously continues like that. This one also continues like that. But if you had x plus 3 squared, then it shifted 3 units that way. So with x, when you're adding something directly to x, the shift is not that logical, I guess, because if you're adding something, you think I'm going to the right, but the effect is actually the opposite. So that means if you add 3, then the graph shifts to the left, and if you subtract, the graph shifts to the right. To scale the graph of the function is to stretch it compress. So compress it vertically or horizontally. Okay, and it's acting up. Okay, so we say that if f of x, or if y is equal to f of x, then c, then y is equal to c of f of x stretches the graph vertically by a factor of c. Okay, and the way it does that is here. If c is greater than 1, then it stretches away from the x-axis, away from the x-axis, so that you can imagine this is your x-axis, and then you pull it up like a rubber band. And then if c is between 0 and 1, then it shrinks vertically towards the x-axis, so it more like compresses it, it gets closer to the x-axis. And then if it's negative, if c is less than 0, there's two things happening actually. There is a stretching happening or maybe a shrinking happening, but then another thing that is happening is that the graph is reflected across the x-axis. Okay, so let's actually see this on some graphs. So we have, again, y is equal to x squared. So if we were to draw our graph, this is our x-axis, this is our y-axis, and this standard graph that we should know, y is equal to x squared. So this is our graph, y is equal to x squared. And then we want to see what does the graph y is equal to 2x squared look like. So c here is 2. 2 is greater than 1, so that means we are stretching it. So this graph, we're going to pull it up by a factor of 2. So it's going to look something like this. So imagine this was a rubber band, and then you stretch it upwards like that. This is the graph, y is equal to 2x squared. So it's like pulled up. And then if we wanted the graph y is equal to a half x squared, so that one is shrunk, so it'll go, I hope you can see the color difference, it'll go like that. It's getting closer to the x-axis, so it's more like shrunk like that. So this is the graph y is equal to a half x squared. And then if we have y is equal to minus x squared, because this is minus 1, it's negative, then it will be reflected in the x-axis. So it's a direct reflection of x squared. So like that. Like that. So this is the graph y is equal to minus x squared. And then if you had something like y is equal to minus a half x squared, so first it's this one here, so it will be this one, and then it's reflected because of the minus. Okay, so when I give you a graph like half x squared, and I say describe the transformation, you have to state the basic function is x squared. So x squared, the one in black, is our starting point, and then it is shrunk towards the x-axis. So we should be able to describe all these transformations that happen to the graph. Okay, there's more examples in the notes which are available on e-learning, so please also go through those. And then the next transformation, we say that if y is equal to f of x, then y is equal to f of cx stretches the graph horizontally by a factor on the c. Okay, so with this one, with when the c is at x, it may be a little bit more complicated, but the way to understand it is that it's not possible to just necessarily stretch it in one direction. Like if I was pulling my graph upwards, I'm also kind of shrinking it sideways. And if I'm stretching it sideways, I'm also shrinking it vertically. So they do affect each other. So for example, if I have the graph y is equal to, what is it, 4x, 4x squared, like this. So you can say, okay, the 4 is affecting the x, but of course this you can write it as 16 x squared, and then relate the transformation that it is stretched 16 units vertically. So they do affect each other, even though here you can write the transformation in terms of x or write it that way. Because when you stretch something vertically, something is happening to it horizontally and vice versa. Okay, so we say here that if c is greater than 1, it is pulled towards the y-axis, and if it's between 0 and 1, then it is pulled away from the y-axis. So like this one here, we do it the way we did above. 4 here is greater than, what is it? It's greater than 1. So it's pulled towards the y-axis. So if your first graph was like that, then pulled towards the x-axis means you are stretching it like that. And that's exactly what was described with the vertical stretching. Okay, and then if c is negative, is less than 0, then it is reflected across the y-axis. Okay, so if it is reflected across the y-axis, that means whatever is on the left goes to the right, whatever is on the right goes to the left, and vice versa. Okay, so note that y equal to the square root of 3x. This is equal to the square root of 3 times the square root of x. So this is basically what I was saying over there. And in summary, we say that horizontal compression may correspond mathematical stretching by a different factor. And vice versa. Okay. Right, so we'll continue in our next lesson and look at exponential and logarithmic graphs, as well as even and odd functions, and then that is what will be in the test.